Hello everybody. Today is my third session about the associations and the dataset and my fourth session overall. Today I will finish up the associations, and next session I will finish up on the dataset and also introduce the query. Now the query is the fundamental mechanism for dataset to query for data, but it is so powerful we can use it in the kernel outside of the dataset function. It is incredibly powerful, and I think you should get really familiar with it. And next session I'll also have a section on getting free data from the web. I call it web scraping, and there are several different methods on how to do that. One method that I just call the traditional method. You can parse HTML, you can parse XML, you can also convert easily HTML into XML, and there are exciting new features available with the new function web execute that Mathematica 12 has. So let's jump into it. Today I will finish up the associations. So today is pretty much only about associations for the entire session, but I do want to bring it to a close and then start moving on to other exciting new features. So let's look at the associations together with two of the most powerful functions that I called Swiss Army knives. They are select in cases, and then correspondingly for cases there's also delete cases. So we can see that select works on the values of the association. Right here we are picking out all elements of the association in which the value is larger than 2. So let's look at a simple application. We want to select only those rows of the Hilbert matrix for which the row total meets a certain criterion. So we define an association that represents the Hilbert matrix, where every row is the value of the corresponding key, 1, 2, 3, 4, 5. And we want to select all the rows for which the total of the row is larger than 1. And we see that this is the case for rows 1 to 3. Let's check on the numeric values. Let's total them. And we see that for the first 3, the row total is larger than 1. For the last 2, it is less than 1. All right, so that's why we're getting 1, 2, 3 here. So this was a case where we selected values based on a criterion. Selecting on values means that the keys are irrelevant, and in this example I deliberately create keys that are not primes. I'm filtering on prime, and squares can never be prime, right? So here you see a case where the key is always a square, therefore never a prime, and every value is a prime. So I use this example to underscore that the keys are totally irrelevant. The same is true for cases. It works on values. So let's look at this association where we have a bunch of numbers and a bunch of letters, and we're only interested in the integers and the colors. So this is what we get, right? 1 and 2 are integers, so they are taken by this pattern matcher. X is not, Y is not, pi is not, blue is a color, and green is a color. So this is what we get. Again, you see that the keys are irrelevant. We only look at the values. All right, let's look into some more complicated examples. For this, I need to define a new association. And let's look at all the sublists from this association. Right? And we see that here we have a list. This is not a list, right? The first one is not. It's an atomic expression. Here's a list, here's a list, here's a sublist, and here's one. All right, so those are the ones that we get as the result of this pattern matcher, where we just filter out by the pattern that we want to list. Give me all 2-element sublists. Well, that is fewer than that. Here's a 3-element sublist, so that's not included. And here's a 3-element sublist, so we don't have it. Right? So we only look at the values. The pattern matcher only applies on the first level. This doesn't have too much to do with an association. This is the way cases works generally, but I want to show you that we can also use association as a head in a pattern matcher itself. So let's look at this a little bit closer. The first example, we are looking for a symbol, and the only solution is the first one. 1 goes to C. We can see that C is clearly a symbol. It is blue and an unevaluated. This association is not a symbol, it's an association. But C is. And if we modify this a little bit for the second examples, we are also looking at symbols here, but again, it is this C and nothing from this association, right? Because that is not a symbol. This is the C that we're getting in the output here. But if we are looking for the association in the pattern matcher, then we get this expression. But given that the first one equals the second element, we get the result only once, right? C goes to C is identical to C goes to C. So here the pattern matcher result is the list of one element association with one element in the association, C goes to C. Right? A cases always returns a list because in principle there could be multiple matches. All right, unless you specify deeper, you can certainly specify deeper nesting levels. And if we use the same inputs, but now we go to level infinity, we suddenly get different results. So we get the C that we had before here. This C is this C and this C is this C. But we now also get B, right? 1 is not a symbol, but B is blue and unevaluated. We get B as a second result. And if we get to the infinite nesting level, then suddenly we can also enter this association. First we couldn't, right? This one didn't show up here, but here we now can. So we're getting this C or this C in this list, right? Depends on the implementation, on how the association does this. Either this is overwritten by this, or this second element is simply discarded because it's the same as the first one. But it doesn't matter because C is C, so we're getting it as well in the list. So when we go down to the infinite level on the association, we get the same result as before, right? It is this association that we had before. All right, so an important difference between select and cases. Select returns the whole matching rule of the association based on the values, and cases only returns the values from the match, not the entire expression. So let's look at this example. We define a new association, and in the case of select, when we are selecting based on even Q, which is a true-false criterion, we get the whole association. If we use cases, then we don't, then we only get the values. And as you know by now, select operates on a criterion and cases operates on a pattern matcher. And with a question mark, we can turn a criterion into a pattern. So all we need to do is say underscore question mark even Q, and we've converted this true-false function into a pattern matcher. Right, so keep this in mind. Here you get the whole expression, here you only get a list of the values. Okay, let's look at a mini application for this. Say we have 11 people who have salaries that go from 100K to 200K in steps of 10K. Right, so we have Stacy has 100K, and up at the upper end we have Camilla has 200K. If we now want to filter out who has more than 150K, so when we ask for select, we get the entire association. If we use cases, we only get the salary levels. We don't know who owns that money. We only get the monetary values. Whereas here we know who earns that money because the association is a key value pair. However, subsequent functions operate on the values, even though part of the return of select was the keys. So if we know total or the salaries more than 150,000, we get 900,000, right? That is operating directly on the values, even though in the case of select we get the whole association back. It doesn't matter when we subsequently operate on it with total, because that is a reducing function. All right, you can also use the associations in the pattern specification itself. So let's create a new list of associations, and if A goes to something in the pattern matcher, then we get the first result where A goes to 1, because A goes to 1 is the only association where A goes to something. But if we say anything goes to 2, then we have 2, right? We have B goes to 2 and C goes to 2. So here we need a list of those 2. So note that we can use associations in the pattern specification. Here we have the association in the pattern matcher and here as well. And note that we can use the underscore for the key and the value. Okay, also interesting I find is that localization is preserved. If we look at this example, then we see that num is green and slanted, and the global num will not be affected, right? So if our global num is 55 and we do a pattern matcher with num goes to 2, then afterwards our num is still 55, right? So we see that we localize it. Num is now cursive, it's green inside the cases. Very useful. All right, the pattern matcher imposes no limitations on the associations. In fact, the key value nature of the association makes the pattern matcher more expressive, I think. So the following example, we find all cases where anything goes to 1 is in the second association element. So let's look at cases of a list of associations, and we find that something goes to 1 is in the second position. Right? This is an association of 3 elements, exactly 3 elements, not more, not less. We don't care about the first one, we don't care about the last one, we only care about the middle element where something goes to 1. So what do we get? Well, we have it in this association and we have it in this association. So you see that this is a very powerful pattern matcher where we can use it with a nesting structure, a list-like structure, and where we can even indicate the specific position in which we want the pattern matcher to happen. Right? This makes it very, very expressive, because here we also have now the choice between key and value, right? Unlike in a list. So you can think of every element in an association as a 2-element expression, right? Like a complex number, which is basically a 2-dimensional number. We don't have that with a list, but the association always contains elements of 2 sub-elements, a key and a value. All right, the condition is a powerful enhancer of cases. So here let's create an association with random numbers for which the key meets a certain criterion. And this time it's the key, right? That's key here. So let's create a list of assos, and then we want to filter out based on the key. The key must be an even number. So here you see the result of these cases is a list of 1-element associations in which the key is always an even number. The above basically says, give me all cases in which the key, which must be even, goes to anything. But we also can, of course, use condition on a value. So here we are now getting a list of only those 1-element associations in which the value is an even number. Note that the above has the whole association in the pattern matcher. Therefore, you get a list of associations. This is handy when you need to match on the keys and values across different associations. Right? See that this is the full association in the pattern matcher here. All right. But often we want to match over the elements of an association, of one association. And if the keys in the list are unique, we can simply throw association around the list. So compare the following examples. again, remember, list of assos is a list of associations that were created with random numbers. So if we now look at this, in the first one, we're looking for the even elements, but we can't, right? Because list of associations is, well, a list of associations, and an association cannot be even or odd. So we get an empty list. Remember, cases always returns a list, because in theory, there can be multiple matches. But there is none. So do we get an empty list? But if we wrap association around it, then suddenly we can get a result. Because when we wrap association around a list of associations, we get a new association. And if we have an association, one association, right? Not lists of them, then we can ask for even odd. So those are the values of that list of associations that have random numbers as their values. Okay, now we do the same with select, all right? And here we get again an empty list because we cannot find even numbers when the list we're testing it on itself is just a list of associations. But we throw association around, so now we suddenly can get results, and we get the same result as in cases, except it's now an association, right? We return the whole expression, not just the values. And are they the same? Yes, they are, right? The values of the select result equals the cases result. That's why values of DD equals BB identically. All right. Okay, so that means if we create this association of a list of one element associations, then we get this one association, right? Where all these sub-associations are merged into one. So the following should result in the same. Here we have an association and we want to find the even values. And this expression here is the very same as above, but we throw association around, and therefore we get the same result, right? You see that this doesn't change anything if we have this valid list of associations. But this obviously cannot work if the keys in the multiple associations are not unique, right? We cannot merge them. We cannot turn list of associations into one association when the keys are not unique. So let's look at this one, an extreme example. So when we have 1 goes to 10 and then afterwards 1 goes to 11, then it's the last one that prevails. And here the second element shows this to a much longer level, right? First 1 goes to 10, then to 11, then to 12, then to hello, then to 27, 1 to 93. So you see this one prevails. All right. And I think this can be a problem, and it can also be a solution. If you use it judiciously and you intend to overwrite earlier keys, then this is a very efficient way to do that, right? But you have to consciously want it. It has to be intended. But if the keys are not unique, this is not a proper way to merge associations into one, and you can have terrible data loss if you just go ahead and throw them together, because later values overwrite earlier values. So you have to be very careful here and use it judiciously, otherwise you can have terrible data loss. It may sometimes be easier with select because the check is simpler, right? It's just a true-false check, not the difference in the following examples. Okay, let's go into this. So the first three basically are just a reminder of what you've seen before, where I'm using composition and right composition and pure function to select the first element. So the first three are all the same. But now look at the next one. I'm throwing an association around this list of associations, and then I take the even. It's this one. And equivalently, we can just select the even numbers from this one association. These are identical, because if we evaluate this association of the list, we get this, right? We get this expression that I use in the second select here. So you see they are identical selections, but here you still get it as the list of associations because you are applying these functions here in a function composition, and here you get this one association of the filtered results. Okay, next I'd like to talk about the listable operations that we have with the associations. They are listable in their values. That means, for example, you can add them, or you can multiply them, or log, or square root, or exponentiate. Whatever you want to do with them, you can use pretty much all arithmetic operations here. So let's look at them. Here we have one association plus another association. So what do we get? We get an association where the values have been added, right? 1 plus 10 is 11, and 2 plus minus 7 is minus 5. We can multiply them, right? What do we get? Well, we get a new association where the values are 1 times 10 is 10, and 2 times minus 7 is minus 14. How about we multiply one association times the log of the values of the second association? And we see it's not a problem, right? And you are reminded that, of course, the kernel uses complex numbers, and therefore we can take the logarithm of negative numbers here. Here's a minus 7. We can easily take the log of it, and then we multiply with 2. And we can take the square root of these numbers, right? Again, here we get a complex result because the square root of minus 7 is I times 7, and then we multiply with the 2. We can exponentiate them, right? Here we have a new result where we have 1 raised to the 10th power is 1, and 2 raised to the minus 7th power is 1 over 128. So you can use the standard arithmetic operations with the associations as well, right? Obviously only on the values. If the keys don't match, however, you can't perform the operation. You can't add b goes to 2 and c goes to minus 7. How would you do that? It's not possible. So in this case, we get the unevaluated input back as output. That's how the kernel regularly treats this. And we get a sensible error message that tells us actually very directly what the problem is, right? The arguments blah and blah and blah are incompatible, right? Not some cryptic error message, but pretty specifically the message that tells us exactly what's going on. And if we hover over association, we see exactly which message it is. It's association : incompatible, right? Great way to troubleshoot bugs in your code. All right, you can apply listable functions directly to the association. It operates, or I think of it as auto mapping the values and no changes in the keys. So compare the following example. So we have an association here where we have different elements going to different values, and we can, I made sure that the values are all numeric results. So we can easily take the sign of these elements, and here you find them, right? These are the sign values of the values in the association. And we can also raise them to the 7th power, right? And here you find the values are the 7th power of the values of the input association. So the sign function and hash to the 7 are pretty similar here. Sign has the attribute listable, therefore this is possible. And hash to the 7 doesn't, but we apply it as a pure function. So we are bingo, right? We can simply use it in this mapping operation. Right? Sign has the listable attribute. So in case I didn't make it clear, mapping and function application happen only on the values. So we can do simple function arithmetic. For example, we can just multiply the whole thing by 12, right? So we get 12 times the values of the association that we created in the first place. All right. Now I come to the association-specific operations. There are now several functions that return the results as associations. One of these functions is counts by. So for example, if I take range of the first 100 integers and I want to count how many of them are prime numbers, I just say counts by, and then I filter out on prime q. That means 75 are not prime numbers, and in the first 100 integers we have 25 prime numbers. Position index is an interesting function because here the elements become keys and the positions become the values. So if you look at this list of letters, we find that A occurs in positions 1, 4, and 6. 1, 4, and 6. The letter B occurs only in position 2, and C occurs in positions 3 and 5. Very useful, right? You see that was list elements here are now the keys. A, B, C, and the counts are the positions are the values in a list. We can group by the second elements, for example, the keys being the elements. So for example, I use group by, and here comes a list of 2 elements, and I'm now interested in the second part. That's what I want to group by, right? So if we look at these ones, the first ones, we find that we have A and B as the first element here, and the second element would be B. So we have B goes to, well, this element, right? It can be multiple, therefore we have an outer list, right? Look at these. And the only one that matches that B is the second element is AB. There's nothing else that has B as the second element. Now, if you want to have C as a second element, there's 2 solutions. AC is one here, and we have BC as a second one that matches it. So in this case, we need to have C goes to, and now comes a list of 2 elements, and that's AC and BC. If we want to look at the last elements of the 2 by 2 Hilbert matrix, so they are 1 over 2 and 1 over 3. That's the right column. And the return, well, everything matches it. So we get the Hilbert matrix again inside a list, right? Again, remember that this is a list simply because it has to be now a value of a group by. And inside that, we find the Hilbert matrix itself. It made no changes. This made no changes to the elements in the list we're working on, right? It just is a clever extraction of how we want to have our keys. And here we have a 2-element list, red, green. We want to group by the second part, so it has to be green goes to, now comes our overall wrapping list, and the element itself, red, green, inside. All right, now we can group by the values of an association. So for example, we take this associations and ask for the even elements. So we have false in the case of A goes to 1, C goes to 3, because neither 1 or 3 are even, and it is true for B goes to 2. Okay, now let's expand this a little bit more. Let's group by prime number. So if we take again a list of the first 100 integers, then it's false for this list. And you will see that this is similar to counts by, right? These 75 here, that's the list length of this list. And it is true for this list, and that's 25 elements. So group by and counts by are incredibly useful functions, but keep in mind, with group by, you're getting your entire input again as an output, and counts by is only a counter, right? You only count how long these lists are. Which brings me to merge, and I think merge is one of the most useful functions in combination with the associations. So, for example, we merge a list of 2 associations and we give a merging function. In this case, I just keep it symbolic. it's a blue G, right? If you look at this closely, it's a blue G. So what this does, it keeps G symbolic in the merge. So we have A goes to G of 1,5 and B goes to G of 210. So as we merge these, we make the A a key, and then the values are 1 and 5. We put them in a list and we wrap G around them. Same with the B, all right? B is now a key. It came from this B and from this B. So we have B goes to 2,10, but wrapped around a G. And now let's pick some specific G's, right? Because this merger function G is actually where most of this power now comes from, because here you can now say what you want to do with the list of these values. So let's create a new one and let's look at some specific merger functions. I think of this as a merger function. Let's look at the total. And now when we just total them, right? If you total 1,5, you get 6. If you total 2 and 10, you get 12. All right, how about we raise them to an exponentiation? So the first element raised to the second. So 1 raised to the 5th gives you 1, and 2 raised to the 10th gives you 1024. How about we take the sign values? Well, now we get these sign values, right? This would be the sign of 1, this would be the sign of 5, this would be the sign of, this would be the sign of 2, this would be a sign of 5, and this would be the sign of 10. Right, did I have this right? Yeah, sign of 1, then 5, then sign of 2, sign of 10. But group based by key, all right? A goes to this list, B goes to this list. And how about we raise them to the power of 5, right? Then we get these numbers. This would be 1 raised to the power of 5, which is 1, and 5 raised to the power of 5 is 3125. 2 to the 5th is 32, and 10 to the 5th is 100,000, right? But keep in mind, we keep the key structure, and they were coming from these different ones, right? Remember, this 1, 5 comes from 1 being a value in the first association and the 5 being a value in the second association. That's why this is a merge, right? Because we're doing it across associations, across the list of associations. All right. Apply no function at all. We can use the identity function. When we want to use the merger function G that does nothing, just keep it as a list, then we use identity. So in this case, there is no G here, right? There is no G that wraps all around it, and we specify this in the kernel by saying identity. So here you get the same 1, 5. There's just no G around it. And here we get the 210. There is no G around it. Incredibly useful. And when you have a third element, right, we now get a new key. I've changed this one here slightly. So we still have 1A because there's only 1. We have 2 B's. Here's a B and here's a B. And C goes to 5. Right, we only have 1, so we get a list of only 1 element. Okay, it's time again for a mini application, and I think identity is the simplest version of a merger function. Who works where after the merger of ABC and XYZ companies? So we have 2 companies. One company is ABC, and in ABC we have Chris working in IT, we have Stacy in accounting, we have Mike in legal, Peggy in HR, and we have Jerome in backups. And in company XYZ, we have Klaus in accounting, IT is run by Jason, Myrtle is in HR, legal is run by Jim, and security by Paul. And after the merger, look how simple this is, right? I just merge a list of two associations, a merge of ABC, XYZ, and our merger function is identity, right? So now we suddenly have Chris and Jason in IT, we have Stacy and Klaus in accounting, Mike and Jim are in legal, Peggy and Myrtle in HR, and Jerome was in backups, but only ABC has a backups group. And we have security and Paul, but only XYZ has a security guy. And that's why you see two element lists for most of them, whenever you have the same department in both companies. But there's only one person in backups, because XYZ doesn't have backups. There's only one person in security, because ABC doesn't have security. Again, I think this is incredibly code efficient, right? You merge the companies and you use the kernel function merge, and incredibly code efficient. Most of the work here was actually setting up the associations that define these companies. How you define ABC and how you define XYZ. The merger operation now is, well, whatever, 20 keystrokes or so, right? So incredibly useful. Okay, now I would like to go to some of the key functions. And I mean, I don't want to beat a dead horse, but you've seen before that these functions, map and automap and cases and select, they work on the values. But sometimes we want to restructure or filter or modify our associations based on the keys, right? We cannot just ignore that. And for that reason, we have functions like key select, key take, key union, and so forth. I think they're very intuitive, and they're very useful because most functions operate on the values, not the keys. So if you want an operation to operate on the keys, you need to use the key ... functions. So let's do again a quick comparison here. We define a new association A to B, C to D. And if we now say key map instead of map, right? We are now key mapping G over the associations. That means map only the keys, don't touch the values, right? Very different from what we did before. And the map is just the map that we've seen before, and you will see that G now operates on the values. And the equivalent short form for map. So here you see G wraps around A, a key, and here G wraps around C, a key, right? A is a key here, C is a key. And with key map, we now have G around the keys. No change to the values, they're still B and D. And in these two cases, it's the map that we've seen before. Now G wraps around the values. So keep this in mind. All you need to do is change map to key map. And now the same thing happens to the keys. You can see that with key map, G wraps around the keys. With map, G wraps around the values. Okay, so now let's look at some more involved examples. Again, I'm creating an association with random numbers up to 20. And let's do the following comparison. When we say key select, where we want odd numbers, then we get an association where all the keys are odd numbers. And here's our typical select, which operates on the values. So now we get an association where all the values are odd numbers. Right? That's why you get different results here based on these random numbers. Okay, let's do another select and key select comparison. In this case, we have all the keys will be prime, and in the typical select case, we have all values will be prime, right? And this one you have only prime keys, and in this one you have only prime values. So you can see with key select, the criterion wraps around the keys, with select wraps around the values. And this logic, this key something logic, percolates through the entire system. So we have key complement, key drop from, key exists queue, and so forth. All in all, it's maybe some, 15 functions or so. So let's look at them. Again, now let's create a second association, right? I call it SO2, because some of these need two associations as input, right? When we have key complement, we obviously need two list-like expressions. When we use key union, for example, right, we need two list-like expressions. So then let's look at some of these key-based functions. All right, in this case we use two. It's probably easier now to have them as a direct comparison. Let's look at SO and SO2. So let's put this always on top, and here we can compare them better. Okay, so now let's look at these outputs. Let's start with key complement. And you will remember from the complement function that we've been using for decades, you can think of this as, in a way, a set minus, right? It's a minus operation on the elements of a set. So it's the keys in SO minus the keys in SO2. And the result is that we are now getting a new association where we have 6 goes to 2 was in the first one, and in these operations of course it has to start with the first one. So we have to take the first element of the first association that we specify here. So that is 6 goes to 2. And in the second association you can see that we don't have any keys of the value of 6. So therefore, given that this is like a minus operation, right, a set-based minus operation, 6 goes to 2 has to be included in the output, right? There is no 6 key in the second association. And the next one would be 7 goes to 14. And it has to be included in the output because there is no 7 key in the second association. 13 goes to 7 would be the third element. But we do have a 13 as a key. 13 goes to 15. So the 13 is not included here. There is no 13 key in the output, simply because it occurs in association 2 as a key. So the next one, 10 goes to 5, well, it has to be included because the second association doesn't have 10 as a key, and so forth, right? In the end, you understand this. Whatever is in association 1 that's not in association 2 as a key has to be included in the output. If the key occurs, like 13 here, 13 goes to 7 and 13 goes to 15, then we're dropping it. This is how complement typically works, right? This is the complement we are familiar with in the kernel. Okay, so now we have to ask if 5 is included as a key in association, and it is. Where is it? We need it as a key. 5 goes to something here. 5 goes to 17. So yes, we get true, right? We get it as true. The corresponding question is key free queue, right? That's the opposite question. So here the question is association free of 5 as a key? And then correspondingly, of course, it has to be false because 5 is included as a key in the association 1. Okay, now we look at key intersection, and key intersection association 1, association 2. Now this one also, now you have to understand this is a bit different now. Here we need to have a list of 2 associations as the output, simply because we have key value pairs. So let's find the intersection that we have. So we have 13 goes to 7, and we have a 13 goes to 7 here, and we have a 13 key here. So we need to have 13 in the list, but they have different values, right? We cannot just take 13 of something, we need to have them separate because we don't want to have any data loss. So we need to say 13 goes to 7 in the first list and 13 goes to 15 in the second list. So the next one, and you can, and you see already that we're proceeding left to right here. The next one would be 1 goes to 18. Here's 1 goes to 18. And it must be in the second list because key intersection outputs it. And we have a 1 goes to something. Oh, interesting. Okay, that's pure coincidence, right? That's pure coincidence. That's the same number. So we have 1 goes to 18 here and 1 goes to 18. That's really a rare coincidence with these random numbers that we have the same value in both cases. So next one, 3 goes to 3. We have that here, and we have 3 goes to something, and here we have 3 goes to 12. That's what we have here as the last one, right? So if they don't occur in both, then they are dropped, right? Then they are simply omitted from the list. Because if they are in one list but not the other, then they cannot be in the intersection. And a good example to see that is if they're listed in the complement, right? So there is no 6 key in either of these two lists. There's no 7 key, there's no 10 key, no 20 key, no 17 key, 18 or 14 keys, right? Because set minus, right, one set minus the other set results in a list of keys that are in one but not the other, which would disqualify them for an intersection. Okay, so I think you now understand key intersection. Key member queue, well, that's also relatively simple. Function is 5 a member of the association. Yes, that's the case. I think the next interesting one is key union. And here I'd also like to spend a little bit of time on it. Again, think about it. The way the kernel operates on these things is left to right. It starts with the first element of the first element. So the first element in this list is ASO, and we start with the first element, and that was 6 goes to 2. So 6 goes to 2 is included in the union, right? We have to find now all the keys, otherwise it wouldn't be a union. But they are not just numbers, they are two element, right? They are pairs. They're key value pairs. And therefore, in the output, we need to get a list of 2 elements. In fact, specifically a list of 2 associations, right? That's what makes it different from just a list, because every list element in an association consists of 2 elements, key and value. So we start with the first one, 6 goes to 2. We have 6 goes to 2 here. And we don't have a 6 in the second association, right? If you look at SO2, you don't find any key with a value of 6. So in the second association, we have to say missing. The key is absent, right? Again, very descriptive reason for the missingness. The key 6 is absent. And if you now go through this, then you will find that given that this is the union, right, where everything needs to occur, and I think the algorithm internally just copies this association as the first one up to the point where things start missing in the first association. So you see this entire association replicated here, because in a union everything needs to occur, and we start with the first one, so we might as well copy it in already. But now have to come the ones that are missing in the first association but are present in the second association. So for example, association 1 has no 0 key. So we have to say key 0 is missing. There's no 4 in the first one, there's no 19 in the first one, and that's it. Okay, and now we come to the second one, and here it's, well, hit or miss, right? So 6 is missing, 7 is missing, but 13 is there, right? We have 13 goes to 15, we have it there. 10 is missing, 1 goes to 18 is there, right? Here we have 3 goes to 12, 3 goes to 12. 9 goes to 5 is there. The 20 key is missing. 8 is there, 17 is missing, 18 is missing, 12 is there, 14 is missing, 5 is there, 2 is there, 16 is there, 0, 4, 19, right? So you get the picture. That all the keys from both lists, from both associations, have to occur in this 2-element list of associations in one way or another, right? Because we're taking the union, not the intersection. So that's why you never have a missing in an intersection, but you can have missing in a union. All right, and key sort. All right, well, so here we get our association back where the elements are sorted by key. 1, 2, 3, a 4 is missing, but there's a 5, 6, 7, 8, 9, 10, 11 is missing, but we have 12, 13, 14, no 15, no 19. All right, so this sorts the elements by the keys, and you will remember that the association is ordered, so it's not a useless operation. Okay, so let's do a comparison of key union against union and key sort against sort with smaller associations. So for key union, here we have a list of 2 associations that what we need for the key union. And if we look at this, we have the first one we just have to copy down, right? It's a union. But we know we can expect from the definition and the behavior that we should get a list of 2 associations. It's the key union. So all the keys have to occur. A has to occur and B has to occur in the first association in the list, and A and B have to occur in the second, right? A and B, they have to occur. It's the union. And if we compare this to the regular union, which operates on the values, then there is a difference, because if now something is missing in the values, it's not a problem, because the values don't have to be unique. They can be unique, but they don't have to be, but the keys have to be unique. So that's why in the first case, we have to get A goes to missing, because in this association, there is no A key. There's only a B key. But we preserve the structure, right? It has to be a list of two-element associations. Not so with a union, because the values don't have to be unique. The keys have to be unique. And with the key sort, well, here we just sorting by the keys, A, B, C. And in the regular sort, we sort by the values 1, 2, 3. Relatively simple. Okay, next let's drill a little bit deeper into key tag. Also incredibly powerful if you know how to use it properly. So with take, we're just trying to grab something from a list or an association. And if it's not if it's missing, if it's not there, what we're requesting, it doesn't matter, right? It's a take, and we cannot take something that is missing, but we're not getting an error message, right? Because there is no requirement like in a union where something would have to be present. In a union, everything needs to be included. So with a take, we just try to grab something, and if it's not there, we proceed, right? Then we don't bother any further. And so if we are trying to take keys A and B from a list of 2 associations, then we're taking A and B as keys from the first one and then from the second one, if present. So in the first one, we have A and B keys, so we just put them in. And again, we give it a list of 2 associations, so our output has to be a list of 2 associations. In the second association, however, we don't have an A key, so we can only take the B key. That's it, right? That's plain and simple, that's it. We are trying to take A and B from this list if they're present, and if they're not present, well, we cannot take them. And if we give it a list of 1 association, so now we're taking A and B. That results in this one, right? Again, we gave it a list of 1 association, so our output is a list of 1 association. C goes to 3, we're just skipping, right? Because we were trying to get A and B, So we don't care about C. So this is the output. Now, slightly different, we key take from an association. This is different, right? This was a list of one association, and here we key take 2 elements from an association of 3 elements. So we get those A and B, but note that this is not a list of an association, this is one association, right? Because this is what we gave it, right? It's the structure that you give it as an input. A list of 2 associations, a list of 1 association, and an association, and this format is preserved, right? Here, this is not a list. Okay, now if we try to grab B and C, well, then we get B and C, right? No A. We're not asking for A, so we don't get it. We're asking for B and C, and there's our output. And please also note that key take has an operator form. So we can simply say, well, take the association, and then in the next step, we want to key take B and C. We don't have to specify any input here. Operator form makes it a bit more code efficient. So we take B and C from this association. Well, it's going to be the same output, right? No surprises here. The operator form doesn't change anything about the computation, so we get the same output as if we didn't use the operator form. So let's look at 2 examples that are a little bit longer. We are grabbing B and C if present. So in the first association, we have them, so we get an association B goes to 2, C goes to 3. In the second association, we have B. We're not asking for D, and we get C goes to 11 in the output, right? So just try to look it up, right? In a way, it's this take here is like a lookup, right? Or a database query. You query for these keys. If they're there, you get them. If there is something you're not querying for, well, then you don't get it, right? You didn't ask for it. And in the last example, we are also looking for B and C, but we are a little bit different here because here we have a C goes to 11, and here in the next example we don't have it in the second association, so we don't get it, right? We cannot try to take something that isn't there. So in this case, the second association is simply B goes to hello. That's what we get because we asked for B. And from the first one, we get B and C. Here they are. All right. Okay, next one, key drop. Also quite intuitive, so I think I just call it no surprises. It works as intuitively as expected. You drop elements with the specified key, right? So we have an association A goes to 1, B goes to 2. We want to drop the key A. What do you expect? Well, it's going to be dropped, and B goes to 2 remains, right? We can drop multiple keys from one SO, right? So here we're dropping A and D. What do we get? Well, A is gone, B is preserved, C is preserved, D is gone, right? We can also drop across multiple associations. So we key drop A and D, and a key A occurs in association 1, so what remains is B goes to 2. And we know from the second association we get a second one, so C goes to 3 remains, because we're not trying to drop it, but we're trying to drop D, and there is a D element, and after dropping it remains C goes to 3. Right? So quite intuitive, you can drop them directly with that. Okay, we can also specify the association as a list, and then it's assumed it's an SO, and then returns an SO. This is also, again, very powerful because it means you can treat lists as associations even though the lists themselves are not associations yet, right? The context key drop makes clear that you are dealing with associations. So when you don't give it an association, well, it just treats it as if it were one, right? So in this case, note that I didn't give it an association, but we are using key drop. So, well, we should interpret this as an association, right? When we have a list of rules, it could be an association, right? So now we're dropping A from this and we're getting B goes to 2, and notice that it gave us an association as the return, not a list, right? We gave it a list, we get an association. We can delete from several lists, right? So here we have a list of 2 associations, and here I have a list of lists. And the elements are rules. This is important, right? Because otherwise you couldn't interpret them as associations. So we are deleting B from the first association. Well, that means only A goes to 1 remains. And if we're deleting B from an association that has only a B key, well, then we get the empty association. And if we're doing it with lists, we get the same result, right? Note that this was a list of associations, this is a list of lists. So same result. A goes to 1 is the first one, and empty association is the second one. We can also delete from a mix of association and rules. And again, those rules are now interpreted as associations, even though they were not specified as associations. So now I'm dropping key B from this expression, and what remains is A goes to 1 for the first SO, and when we delete B as a key from the second, then we get C goes to 3 in the second SO, right? So we get a list of 2 one-element associations after deleting B from here and from here, right? Again, this is a mix. This is an association and this is a list, but they're treated the same. And key drop has an operator form, so these two are equivalent, right? If we are deleting A and D keys from this association, or if we are asking key drop of A and D from this association, which are the same association, but we're specifying key drop differently, it gives us the same result. Okay, very important, there's a function key drop from, and that changes the association. Can be very dangerous. So here I give it an association, A goes to 1, B goes to 2. And if I key drop from A from the association, then I get B goes to 2 as the association itself, right? The first one here, this is just the output of key drop from, but that doesn't show us what association itself is, right? We just delete it and that's just the output from it. When we inspect association itself, then we get B goes to 2, right? Very important. So keep in mind, key drop from changes the association, it modifies it. Key drop does not, right? Key drop just applies this operation and gives you a new expression. It didn't change the association itself. This one here is still the same association afterwards. We just don't look at it, right? But if we have a named symbol for it, it changes the association. Similar to what you know as append to or prepend to, they change the underlying expression. So here another example. We have a new 4-element association, and we are dropping elements A and D, and then we look at the association itself after the operation and it has changed, right? Okay, all right, I'm coming towards the end of this session. I want to show you various bits and pieces and some loose ends that I have collected over the years. Nested lookups of values are associations themselves. So we look up A, that gives us an association, and then we look up the second key. Look at this one, look at this example. We first look up A, and what's the return of A? Well, it's gonna be this, B goes to Z. And then we look at B of that, and what's B, the return of B from B goes to Z? Well, it's Z, right? So in this case, we get Z in both cases. We can do it in part style, and we can do it in function style. Same output. We never requested C, so we don't get Y, right? But we get A first, and then we look up B. So we have nested lookups in the associations. And again, you can use part style and function style. A rule for the association in a list is flattened or merged, right? You see that B goes to 2 is just a rule, but A goes to 1 is in a separate list, right? But what do? We don't care. We treat them the same. The first list here is just flattened out so that we get A goes to 1, B goes to 2, so they are association elements on the same level. An association on the element level of an association is merged as well, and remainder duplicates are removed. So here we have just typical element, and here we have an element that wraps association around it. But this is merged as well, because we don't care that we specify this as an association. We're inside an association anyway, right? So why should this be an association wrapped around it when we want to have an association there? It has to be an association anyway because of the outermost function here. So this context, right? This context of an outermost association tells us already that we just want to splice these in. So we get one association of these 4 elements. Right here we have a B goes to 2, which overrides, right? Duplicates are removed. So this is no different from this in the outermost association context. So when splicing this in, this doesn't make a difference. But this one does contribute new elements, right? Because C and D are not in the list yet. So we just get them as the 3rd and 4th element. And I think this can encourage sloppy programming, right? You may leave something as an association when in theory you shouldn't, but it can also be very programmatic, right? Again, this is the two-sided sword that I had mentioned earlier. If something makes it easy for you, then it can be a good thing if you consciously use it. But if it makes you sloppy, then it can be a dangerous thing. I think sloppiness can be very practical if used consciously, and not just due to laziness, right? You have to be careful on what you want here. You can be sloppy and leave those associations around here, but don't let that encourage you to be sloppy. But if you use it intentionally, then by all means, right? It makes your programming easier. All right, but obviously if a key or value of an association, then it must be kept. So this here is different, right? This one here is an association where it's a value. Here the whole element was an association. Here it's only the value. And in this example, I have the association as a key, right? The whole thing here is association goes to. Obviously, association can be keys and values. So in this case now we have here an association as a value, and we have an association as a key in this case. All right, so note that this is different. Value, here it's a key, here it's just an element on an association level. Okay, we can also use extract on associations. I think extract is another very powerful function. We can obviously use map inside the association. The map is evaluated first, and all the other functions that the kernel is aware of. So here I'm defining an expression in a rather complicated way. So the first element we have 1 goes to a polynomial in X. The second one is a polynomial in Y, and I've written this. I've created this polynomial in a rather complicated way, right? I map a range from 0 to 4 over Y to the exponent. 3 also goes to a polynomial, the sum of all the z raised to the i-th power, where I goes from 0 to 9 in steps of 3. That's what you see here. And 4 goes to a rather complicated way to generate a very simple list, right? I could have created this much easier by typing it in or doing other computations. Instead, I chose a very complicated form to show you that the mapping operation happens first, right? These are evaluated first before they become keys and values. and 5 goes to a list of tangent plots. Okay, I now want to use extract and show you how extract works together with the associations. So when we have only one key, then it doesn't matter if we wrap it in a list, right? We can just request the first key directly or put that in a list. And the first key was 1 goes to the polynomial in X, right? This is our first key. First key is 1. Okay, but now we want to go deeper and get every sub-element, right? Here we can get sub-elements into this based on its position, which then becomes a list of monomials, right? A polynomial is a sum of monomials. Now we have to specify the indices in the position list. So, for example, if we now map on key 1 on the levels 1, 2, 3, 4, then we get the monomials, right? Because this is just a sum of monomials. And if we now extract on this element level, right, we're going to key 1, but then here we're going, the hash goes through the numbers 1, 2, 3, 4. Then we get these 4 sub-elements. All right, let's look at key 2. You remember that key 2 was the polynomial in Y, and it has 5 elements. So I'm throwing 1, 2, 3, 4, 5 through the slot. So we're getting these monomials. Right? The polynomial was the entire sum, and the monomials, this is the list of the monomials. All right, let's look at 3, and that was the polynomials in Z. So I'm going through slots 1, 2, 3, 4, and here are the 4 elements. Okay, key 4, well, that was our complicatedly generated list. Again, let's look at it. 0, 1, 2, 1, 0, 1, 2, 1, 0. Right? We're going from 0, 1, 2 up, and now we're going down, right? It's like a triangle curve. 0, 1, 2, 1, 0, and now we do again 0, 1, 2, 1, 0, 0, 1, 2, 1, 0. And if we look at them here, I can now also look at these elements. And if I only focus on the zeros, well, I mean, I know how I've constructed it. It has to go from 1 to 17 in steps of 4. Then the second one was always a 1, so I start at 2. And the third one was always 2, so I start on index 3, all the way to the 17 in steps of 4. So, of course, here I get 5 zeros, and then I get 4 1s and 4 2s. Right? So I hope this makes clear that first you specify the key in this list, and then you go through the sub elements with the slots here in this position. Okay, we have 5, and okay, this is perhaps not so exciting because we just get a list of these elements again, right? This is not too exciting. Here it was an association. 5 goes to the list, and here we just get the list, right? So here this is not too exciting. I just picked the list of the tangent functions to show you that map is evaluated first, right? Here, this map to generate them before it becomes an association. Keys and values are evaluated first before the association is constructed. Expressions are evaluated first before the keys come, right? So again, a very complicated way to here, right? This is a list and goes to a list, and ABC is pretty simple. Those are the values, and this here is a complicated way to just create 0, 1, 2. So again, we evaluate the expressions first before they become the keys or values. In other words, first before they become associations. Okay, and you find more info on Stephen's page on Assos in his elementary introduction, right? If you still need to look at an elementary introduction, have a look at this link. I think I've gone way beyond this elementary introduction. What I showed you was not elementary anymore. But I think for you to become a good data scientist, you just have to get familiar with the associations. They're just so powerful, and they're now fully integrated in the system. And one way to see that is that the kernel itself now returns several things as associations. You've seen that with group by, right, or position index, and counts by, right? So I think you can see by the fact that this kernel itself returns you answers as associations that associations for you are inevitable. You cannot escape them because some functions already return them as associations and you don't have a choice. All right, this brings me at the end of today's session. I hope I see you next time. Thank you. Bye-bye.